God, this is going to be an editing nightmare. Okay. The North Pole, the top of the Earth, at least relative to how it's spinning, is different than the magnetic North Pole. Both of them are in the same kind of polar region, but following a compass north will not get you to the North Pole. Not even close. In fact, this kind of historical terminology for magnets, the words North and South Pole, are kind of a historical accident. Exactly where the Earth's magnetic North Pole is not really all that important. I mean, first of all, it's on the move kind of constantly. And secondly, the Earth's magnetic field is not a perfect dipole. But for most navigational purposes, it's, good enough. Unless you live in the Pacific Northwest. Out here, there's a pretty large error. The discrepancy in the Methow Valley, for example, between magnetic north and true north on a map, is something like 16 degrees, 18 minutes. To navigate with a map and compass out here, we need to make sure that we're making this correction kind of on the fly. In other words, we need to translate between perspectives, between the perspective offered from the map and the perspective offered from the compass. From the perspective offered by the geographic Earth to the perspective offered by the geomagnetic fields of the Earth. By and large, both of these perspectives are totally valid. You just have to be careful about mapping between them. If you're traveling with a map and compass, you need to make sure that you're translating between them appropriately. And if you're trying to talk with other folks, you also need to make sure that you're speaking from the same perspective. Fortunately, that perspective shift is an easy one to discuss. It's just a rotation by a little bit more than 16 degrees. For most purposes, this rotation fixes a lot of the error between magnetic north and true north. Magnetic north mixes a lot of true north in with a little bit of true east. Or vice versa, true north can be thought of as a mixture of a lot of magnetic north and a little bit of magnetic east. At least out here. The one thing you do have to be careful though is as you move further north or further to the east, west, or heck, even south, that mixing angle changes just a little bit. In any case, this idea of mixing directions together is a really convenient way to discuss rotations. Speaking of rotations, if you're a pilot of a plane or a boat, you probably understand a lot about rotations. Three-dimensional objects like planes, people, or even bison can rotate in three separate ways. We often call them roll, pitch, and yaw. Roll is a rotation that takes you from side to side. It's kind of like shifting your weight from one foot to the other. Pitch rocks you back and forth like you're going from your toes to your heels and back. Pitch is totally fine if you're on a boat, but roll? Not so much. Yaw is a little bit harder to explain to a bipedal individual. If you were a quadruped, it might be a little bit easier. The best way to think about it is to try to turn around behind you and see what's back there. That's yaw. If you're experiencing a lot of turbulence on a plane ride, yaw is probably the least comfortable of the three rotations that you're experiencing. So there are three separate, independent ways that you can rotate in 3 dimensions, and each one of them can be thought of as a rotation on a compass dial, in a manner of speaking. In 2 dimensions, you recall, we have north, south, east, and west. So following centuries of mathematical tradition, let's call north-south y and east-west X. To rotate that compass dial, we can start, say, with X, start facing east, and start rotating a little bit to the north. Just add a little bit of Y, and then a little bit more, and then a little bit more, and then a little bit more, and eventually you're facing to the north. In 2 dimensions, like on the surface of the Earth, you can really only rotate in one kind of direction. In 3 dimensions, we also have up and down. For lack of a better name, let's just call it Z, or Z if you're British. Now we have all kinds of options. So we can start with X and we can add a little Y, or we can add a little Z. In other words, if you're facing east, you can turn a little bit to the north, or you can turn a little bit to look up. So many options. In fact, there are 3 ways that we can pair these 3 cardinal directions: X with Y, X with Z, or Y with Z. Well, it's a little confusing, right? Yeah, kind of like that Joker who gives you directions to some place by saying, hey, turn left at the tree and then take a right and then take the second left, without telling you from which way you're coming from or what the names of any of the cross streets are. It's all relative, and that's kind of the problem, which is why on a map, like for the Earth, when we want to communicate, we often define cardinal directions, north, south, east, and west. Because up and down, left and right, forward and backward are really only suitable for our personal perspective from our, personal frame of mind. I mean, even when we talk with each other, facing each other, we often say things like your left or my left. And in doing so, we are actually making that mental rotation in our head of 180 degrees when we're switching from one perspective to the other. Great, so I'm sure you're wondering at this point, what does any of this have to do with special relativity? Well, Einstein's great idea was that we are not living in a 3-dimensional world, we are living in a 4-dimensional world. X, Y, Z, and T. T for time. Time, in other words, is just as valid a concept of dimension as is space. As we briefly mentioned in our discussion of cosmogenic muons, special relativity affords a way to mix space and time dimensions together. Rotating space with time means that people or particles will have different perspectives on what time is and what space is. Just like how magnetic north is actually an admixture of true north with a little bit of true east, one person's version of space and time can be different from someone else's version of space and time by mixing their concept of time with their concept of space. Wild, right? Well, let's just see how this might work. So, in 4 dimensions, X, Y, Z, and T, let's see how many different combinations of directions we have. So we have the familiar ones from 3-dimensional space, from X, Y, and Z, but now we have 3 more. In other words, we can rotate any of X, Y, or Z together with a little bit of time. So, in other words, in 4 dimensions, there are 6 independent ways to rotate, 6 independent concepts of rotation. But wait, hold on, let's step back a little bit. What does it even mean to rotate between a space dimension and time? Space and time are 2 totally different things, right? Well, here's a physics formula that you're probably familiar with. Distance equals rate times time. So, in other words, if you're traveling at a constant 60 miles an hour and you go for 1 hour, you'll go 60 miles. For 2 hours, 120 miles. So this gives us a sense of how we can start to think about mixing space dimensions with time dimensions. When we rotate from one spatial direction into another, from like east into north, or from, straight ahead into left or right, we often talk about this in terms of angles, like just on the compass. The same is true, of course, for any of the rotations in 3 dimensions. We, go from 0 to 360, and that brings you back. You just go around and around and around. For rotating time and space, things are slightly different. The parameter of that rotation isn't an angle, it's the velocity. And the velocity takes values from 0 all the way up to the speed of light. I guess in any direction, you can go from minus the speed of light to the speed of light. It's a little weird, but it kind of has the same effect as a rotation. When we see an object moving really, really quickly, either at us or away from us, its time slows way down and its length is distorted. So what does it mean to mix space and time? Like, what are the actual implications? Well, the first one is pretty straightforward. We are all constantly in motion, at rest, at the speed of light, through time. We are moving through time at the speed of light. That's it. When we actually see objects in physical motion through space, we're seeing their speed. And by seeing their speed, we're actually seeing that speed as kind of that angle of rotation between time and space. Of course, observing these kinds of effects, these rotations in space and time, are really only applicable to objects that are moving really close to the speed of light, not for everyday things like walking, running, driving, or flying. Seeing time slow down for items in motion is sometimes called time dilation. And as you might recall from our discussion of cosmogenic muons, it's crucial for understanding why those particles, which should decay after 2.2 microseconds, can make it all the way down to the surface of the Earth. Because from our perspective, they're flying at us at 99.5% of the speed of light. So their time, from their perspective, slows down considerably, meaning that they can live, from our perspective, for up to 10 times as long. There's a complementary effect to time dilation that has to do with the size of the objects that are moving. Since motion causes objects to rotate between space and time, you might expect that some of an object's length might inadvertently get rotated into time. It's true, the bus that's driving towards you at a certain speed appears to you, just standing there, like it has shrunken just a little bit with respect to, say, the perspective of the driver of that bus. This complementary phenomena is called length contraction, and again, really only matters if you're going to be traveling at speeds close to the speed of light. But this does happen with nuclei that are traveling very close to the speed of light, like we saw with cosmic rays. Do you remember that a tiny fraction of those cosmic rays were actually nuclei of, say, oxygen or even iron atoms? From our perspective here on Earth, when they collide with molecules in the upper atmosphere, they've actually shrunken down to a little pancake worth of a nucleus. For a more understandable, controllable situation, you might consider it a human-caused source of this kind of length contraction. For example, at the relativistic heavy ion collider in Brookhaven, Massachusetts, they accelerate gold nuclei up to extremely, extremely fast speeds and then smash them together. And in the process, you get these two little pancakes of nuclei smashing together, just to, see what happens, see what's inside. But remember, time dilation and length contraction are just kind of a change in perspective. Nothing physical is happening. Nothing's actually changing shape or size. Everyone just sees the world from their own perspective. It just so happens that perspectives don't have to be the same. They depend on our relative velocities, hence the name relativity. So you might ask, well, how far does this sense of individuality extend? How insular is our perspective of the universe? Is our sense of reality? Well, don't worry. We all still agree on the same basic set of facts. And here's where our discussion of rotations can really help with your intuition. Consider a coffee mug. If I rotated this coffee mug, the logo on the front doesn't really disappear. Nothing's changed. I'm just seeing a different side of the mug. It's just a change in perspective. The same is true with rotating time and space. You're just seeing a different perspective on the same reality. But there is one implication that's a little hard to wrestle with. The order in which things happen in our universe isn't necessarily the same from everyone's perspective. To really get a feel for how order and perspective work together in special relativity, it helps to have a physical example. So let's consider a track race with a photo finish. It looks like both runners cross the finish line simultaneously. As it turns out, who won the race kind of depends on your perspective, on what speed you're moving relative to the finish line. Remember, space and time can be rotated into each other. Crazy, right? But if you travel near the speed of light, this kind of rotation might be more intuitive. MIT's Game Labs produced some fun material to give you a visual sense for this effect. But just knowing that the order in which events can happen depends on your perspective from your frame of reference kind of makes you think, doesn't it? Maybe even panic a little bit. I mean, does that mean that the past and the future are flexible? Can I go back in time by traveling really, really, really fast? No, of course not. Nothing travels faster than the speed of light, and that includes cause and effect. Yes, it's true that who won the race depends on your perspective, but cause and effect are still a crucial part of reality. Again, this is just like the logo on the coffee cup. We're just seeing two separate perspectives on the same reality. To illustrate this, let's kind of look at it graphically. Time versus space. If the camera is in the middle of the track, it can shoot out light in either direction, and this breaks space-time into two parts, inside and outside. Cause and effect live inside that triangle. I can send instructions or with a laser, say, or with a cell phone, but I can only do that from inside. Outside this triangle or light cone, hey, it all depends on your perspective. Wikipedia has a great animation of this effect, which might also give you some sense for how velocity, speed, rotates between space and time. So if you're going to have a track race in the future where people can run really, really, really fast, make sure you set the rules correctly. That is, you need to say that it's whoever crosses the finish line first from the reference frame of the finish line. And if you're going to have a camera, make sure that that camera is at rest and that that whole finish line is within the causal triangle or light cone of that camera. And that completes our whirlwind high-speed tour of special relativity. Hopefully that kind of gives you a little bit more sense of why cosmic muons, which should decay in 2.2 microseconds in the lab, actually make it all the way down to Earth in a time that takes over 10 times as long. It's rare and kind of magical to have a concrete manifestation of special relativity in our day-to-day lives, in something that's happening all around us, and that's part of the reason why I wanted to share all these stories from particle physics with you. Anyway, more to come, physics friends. Thanks for watching.
Baby, one day I'm hoping that